During some chemical reactions, chemical species lose or gain electrons and oxidation states of elements increase or decrease. Oxidation state is the charge an atom or ion acquires when it totally loses or gains electrons, or for an atom in a covalent compound, the charge the atom would have if all of its bonds to other atoms of different elements were completely ionic. For elementary chemistry, the terms oxidation number and oxidation state are used interchangeably. Oxidation and reduction are opposite processes which always occur together. Reactions in which these processes occur are called redox reactions. Fundamentally, oxidation refers to the loss of electron or electrons by a molecule, atom, or ion, resulting in an increase in the oxidation state of a particular atom, while reduction refers to the gain of electron or electrons by a molecule, atom, or ion, resulting in the decrease in the oxidation state of a particular atom. It must be noted, however, that oxidation and reduction properly refer to a change in oxidation state, as the actual transfer of electrons may never occur. Modern definitions of oxidation and reduction recognize the total or partial transfer of electrons and the resulting increase and decrease in oxidation state or number of the elements involved. Total transfer of electrons usually takes place under ionic conditions, for example, metal to nonmetal, and partial transfer in covalent conditions, such as between two nonmetals. Where atoms of nonmetals of different electronegativities are covalently bonded together, the shared pair of electrons is pulled closer to the more electronegative atom, which results in its reduction. The less electronegative element partially loses the bonding electrons to the more electronegative atom and is oxidized. The traditional definitions can be explained in terms of this modern idea. For copper to gain oxygen, each atom of copper has to lose 2 electrons to each atom of oxygen. Hence, the copper is oxidized as its oxidation state increases due to the loss of electrons. One, the oxidation number of all elements in their free state is 0. Example, aluminum in the solid state has an oxidation number of 0. Oxygen atoms in O2 gas have an oxidation state of 0. Nitrogen atoms in N2 gas have an oxidation state of 0. 2. The oxidation number for elements that exist as ions in ionic compounds will be the same as their charge in the compound. When writing oxidation state, it is written with the sign preceding the state to prevent confusion with the charge on the ion, which is written with the sign after the state. For example, in the case of sodium chloride, the charge on the sodium ion is 1+, but the oxidation state of sodium is +1, and that of chloride is -1. 3. The oxidation number of elements in covalent compounds or radicals is the actual charge the atom of the element would acquire if all their bonds to other atoms of different elements were totally ionic. For many elements, especially transition elements, this number may vary from compound to compound. For example, in manganese 4 oxide, MnO2, the oxidation state of manganese is +4, but in potassium manganate 7, KMnO4, the oxidation state of manganese is +7. 4. The sum of oxidation numbers of elements within a compound is 0. While the sum of oxidation numbers of elements in a radical is equal to the charge on the ion. Five, the oxidation state or number of hydrogen is +1 unless in the hydrides of metals where it is -1. 6. The oxidation state of oxygen is -2 except in peroxides or superoxides. 7. When two nonmetals form a compound, the more electronegative element has the negative oxidation state. Example, in hydrogen fluoride, the oxidation state for hydrogen is +1, whilst fluorine is -1. 8. The usual oxidation states of elements in the groups of the periodic tables are as follows. Group 1 elements, +1. Group 2 elements, +2. Group 3 elements, +3. Group 4 elements, +4 when bonded to a more electronegative element, and -4 when bonded to a less electronegative element. Group 5 elements, -3 as simple anion, but varies when part of a radical, usually between -3 to +5. Group 6 elements, -2 as simple anion, but varies when part of a radical, usually between -2 to +6. Group 7 elements, -1 as simple anion, but varies when part of a radical, usually between -1 to +7. A radical in this case refers to a polyatomic ion. Example 1. Let's find the oxidation state of nitrogen in magnesium nitrate. First, remember that the sum of oxidation states of all elements in a compound is 0. So if the oxidation state of magnesium is +2 and the oxidation state of oxygen is -2 times 6 equals -12. Assuming the oxidation state of nitrogen is x times 2, which is 2x, we can form the equation +2 plus bracket -12 plus 2x equals 0. This resolves to calculate the oxidation number of phosphorus in phosphorus acid H3PO3. Oxidation number of hydrogen is +1 times 3, which is equal to +3. Oxidation number of oxygen is -2 times 3, -6. Assuming the oxidation state of sodium plus oxygen to give sodium oxide. Sodium gained oxygen by losing electrons to oxygen, resulting in an increase in the oxidation state of sodium from 0 to +1. Therefore, oxidation has occurred. The resulting electron gain by oxygen has decreased its oxidation state from 0 to -2, so oxygen was reduced. The reaction is therefore a redox reaction. Example 2. Copper oxide plus hydrogen gas to give copper plus water. Copper oxide lost oxygen, and this is reduction. Hydrogen gained oxygen, and this is oxidation. Hence, the overall reaction is a redox reaction. Example 3. Potassium iodide plus chlorine gas to give potassium chloride and iodine. Oxidation numbers. Potassium in potassium iodide +1, iodine in potassium iodide -1. Chlorine in chlorine gas 0. Potassium in potassium chloride +1, chlorine in potassium chloride -1, and iodine in the solid 0. Iodine has been oxidized since the oxidation number of iodine atoms increased from -1 to 0. Chlorine has been reduced since the oxidation number of the chlorine atoms decreased from 0 to -1. Example 4. Magnesium plus sulfuric acid to give magnesium sulfate and hydrogen gas. The oxidation number of magnesium increased from 0 to +2, so magnesium was oxidized. The oxidation number of hydrogen in sulfuric acid decreased from +1 in H2SO4 to 0 in H2 hydrogen gas. Therefore, the sulfuric acid was reduced. An oxidizing agent or oxidant is a substance that causes oxidation in another substance by accepting electrons from it, and as a result, the oxidation sodium, potassium, etc. are very good reducing agents as they lose electrons readily, and halogens like chlorine and fluorine are very good oxidizing agents as they are very electronegative and gain electrons readily. In the reaction zinc plus copper sulfate to give zinc sulfate plus copper, zinc is the reducing agent and is therefore oxidized. Zinc loses 2 electrons to give Zn2+. There's an increase in oxidation number, therefore oxidation occurred. Copper sulfate is the oxidizing agent and is reduced. Copper 2+ gain 2 electrons to give copper solid. Oxidation state moved from +2 to 0. There's a decrease in oxidation number, therefore reduction occurred. Zinc is a reducing agent as it caused the reduction of copper 2 to metallic copper, while copper 2 ions is the oxidizing agent as it caused the oxidation of zinc from its metallic form to Zn2+ ions. In this case, the sulfate 6 ion is considered a spectator ion as it did not undergo any redox change. In the reaction, manganate plus 8 moles of hydrogen ions plus 5 moles of iron 2+ ions to give 1 mole of manganese 2+ ions plus 4 moles of water and 5 moles of iron 3+ ions MnO4- is the oxidizing agent, as the oxidation number of manganese in MnO4- decreased from +7 to +2 in Mn2+, and MnO4- is therefore reduced. Iron 2+ loses an electron, and therefore its oxidation state increases from +2 to +3. Hence, it is oxidized and is therefore the reducing agent. Composition of an electrolyte by the passing of an electric current through it. An electrolyte is usually a molten ionic compound or an aqueous solution of an ionic compound or a covalent compound that ionizes in aqueous solution. The current is thus conducted by mobile ions in an electrolyte, electrolytic conduction, as opposed to mobile electrons, which is what occurs in metals and graphite, which is known as electronic conduction. During electrolysis, the cations and anions in the electrolyte migrate to the oppositely charged electrodes. Cations being positively charged migrate to the negatively charged electrode, the cathode. Conversely, the anions being negatively charged migrate towards the positively charged anode. At the anode, the positive electrode, oxidation takes place as anions lose electrons to the anode. At the cathode, the negative electrode, reduction takes place as cations gain electrons at the cathode. For example, the electrolysis of dilute copper sulfate solution using carbon electrodes. At the cathode, both copper 2+ ions and hydrogen ions from the water are attracted to the cathode, where copper 2 ions are preferentially discharged as they accept electrons and are reduced more readily than hydrogen ions. Copper 2+ ions gained electrons, therefore reduction took place. At the anode, both sulfate and hydroxide ions from the water are attracted towards the anode. However, hydroxide ions will be discharged preferentially as they give up electrons and are oxidized more readily than the sulfate anion. Hydroxide ion lost electrons, therefore oxidation took place. Tests for these reagents depend on reactions which involve changes which can be detected readily. These changes usually involve the production of different colored or colorless substances, precipitates, and/or gases that are then identified. Known oxidizing agents are used to test substances for reducing properties, and known reducing agents are used to test substances for oxidizing properties. Oxidizing agents may be identified by their reaction with the following known reducing agents. A. Iron 2 sulfate in the presence of sulfuric acid solution. The iron 2 sulfate is acidified with sulfuric acid to prevent the aerial oxidation of iron 2 to iron 3. For oxidants or reductants that need to be acidified, a mineral acid with little oxidizing or reducing tendencies, such as dilute sulfuric acid, is used. Reducing agents may be identified by their reactions with the following known oxidizing agents. A. Acidified potassium manganate 7. Note well, the solution is acidified with an acid which has little tendency to be oxidized, such as dilute sulfuric acid. Hydrochloric acid would be unsuitable as it would readily be oxidized to chlorine. A high concentration of hydrogen ions is required to drive the reaction to completion, otherwise a brown precipitate of manganese dioxide will result instead of the pale pink manganese 2+. The manganese 2+ ion presents as colorless in low concentrations. B. Acidified potassium dichromate. As oxidizing and reducing agents. Generally, these substances function as oxidizing agents in the presence of a stronger reducing agent than themselves and vice versa. For example, A. Hydrogen peroxide oxidizes iron 2 ions to iron 3 ions but reduces acidified manganate 7 solution to colorless manganese 2 ions. It acts as the reducing agent when it reacts with a stronger oxidizing agent, potassium manganate 7. Any redox reaction is made up of two half reactions. In one of them, electrons are being lost, an oxidation process, and in the other one, those electrons are being gained, a reduction process. The first step is to write separate balanced ionic equations for the oxidant and the reductant. These equations are called electron half equations or ionic half equations, or most commonly half equations. The second step involves rewriting one or both half equations so that the number of electrons used to balance each equation is the same. This step is to be omitted if the number of electrons on opposite sides of both half equations is the same. The third step is to combine the half equations into one by removing the chemical species that occur on opposite sides of both equations and rewriting the remaining species as one equation. Example: the reaction between hydrogen peroxide and acidified potassium manganate 7. Step 1 for the oxidant. MnO4- is the oxidizing agent and it is converted to manganese 2+ in the presence of hydrogen ions. Hence, MnO4- plus H+ to give Mn2+. The equation now needs hydrogen and oxygen on the right-hand side in order to be balanced. Water would be formed from the hydrogen ions and the oxygen atoms from the manganate 7 ion. Hence, MnO4- plus H+ to give Mn2+ plus H2O. Balancing the atoms will result in MnO4- plus 8H+ to give Mn2+ plus 4H2O. Now that all the atoms are balanced, the charges need to be balanced. Currently, there are 1- and 8+, which is equal to 7+ charges on the left-hand side, but only 2+ on the right. Therefore, 5 electrons need to be added to the left-hand side to reduce the 7+ to 2+. Step 1, the reductant. Hydrogen peroxide is oxidized to oxygen. Hence, hydrogen peroxide plus oxygen gives 2 moles of hydrogen ions. In this case, all the atoms are balanced and the charges now need to be balanced. In order to balance the charges, 2 electrons need to be added to the right-hand side of the equation to make the overall charge on both sides 0. Step 2. The half equations are